Hello, hello, hello。喂喂喂喂喂，有，好，hello。Okay, so good afternoon. Welcome back to DSP, and thank you for staying with me till almost near the end of the semester. Thank you very much, okay, for coming here into the classroom for learning. Okay, that's not easy. So today we will have 1 hour of a lecture, as I promised. And the topic will be what we call optimal approximation. So we are going to still design an FRR filter, low pass or high pass or band pass. But now we have a new approach, not using windows. Okay, we are not going to talk at all about any windows. Still designing FRR, but not using windows at all. Okay, this is an entirely different approach by the name optimal approximation. So let me just give you a bit of an overview. So let's say if we are still interested in, for the case of low-pass filter with what? Cutoff frequency and the transition band. Let's say this is the frequency at which the stop band begins. Okay, so omega s. S stands for stop. Okay, omega c cutoff, omega s stop band. So gain should be 1 in the pass band, 0 in the stop band, all the way until frequency pi, which is Nyquist. Okay, so very simple, still the same idea. But now, the idea is that we are going to define a tolerance scheme. Okay, remember that in the stop band and pass band, we allow some tolerance. Tolerance of what? Tolerance of ripples, right? So we are going to introduce, let's say this is the ideal response, 1 and 0 for 2 bands. Let's say this is the ideal response. And let me take a preview of my notations. So the ideal response is denoted as H desired. No. A, is it? H desired, okay? Suppose we have a desired response. D stands for desired, 想要的, desired. So definitely this is the desired response. And here, we're going to introduce a kind of weighting function, big W. Let's say we are going to have the weight of 1 for pass band and perhaps 3 for stop band. Okay? For example, weight function. And then the error is defined as the difference, design error, right? Weighted design error. Can I say that? Okay. Suppose that the result of our frequency response is denoted by A, just for simplicity. A is the result. Okay, the result of our design. So let's say, yeah, let me actually reread this first line. Okay, so we have a constraint. The constraint is that our filter is type 1. Okay, type 1 zero phase. That means this. Suppose that our filter has this symmetry. Okay, h minus n equals to hn. Okay, where n is a range from between minus big N and plus big N. Okay, so when you just write down the frequency response using DTFT, this is just nothing but DTFT. Okay, using DTFT to obtain the frequency response, and then h0 is there. But then, because of this symmetry, so you'll end up with this notation, this expression. Okay, so the frequency response, it looks like, of course, it relates to all the sample values, h0, h1, 2, 3, 4, 5 to hn, and where h minus n equals to hn. Okay, so this is a general expression for all possible frequency responses, given the filter samples in the time domain. Okay, nice expression. So now we are going to define the error function in a weighted manner. Okay, so we're going to first calculate the difference between the desired response, right there, ideal response, so to speak. Ideal response will be different from your design, right? Your design is never perfect. Okay, so there's a difference. But then we are going to weight the difference. Weight, 就是权重啊。Not to waiting for somebody, but weighing two bands differently. So W, for example, I'm going to give it a weight of 1 for pass band, a weight of 3 for stop band. Okay, and then we call the result, and the result is, of course, going to be a function of frequency. So far, so good. So, for example, let's say somehow you construct a filter and its frequency response turns out to be like that. And I don't know, just drawing some random picture. And then that. Okay, not a good approximation. For example, if somehow we design a filter which has this behavior, and this is A of omega, your design, right? Of course, it's different from the ideal. And then what's going to happen is that we are going to, by saying that E, the error function is weighted between, take the difference, HD, and our design. So for each design, we can calculate this as a function frequency. And then what we care in this optimal approach, the important thing is that in this optimal approach, the objective function that we're going to minimize is the maximum of weighted error. Of course, we take the absolute value, because plus or minus. I mean, positive or negative, we take the absolute value, and we care about the maximum weighted error, and we want to minimize it. Is that clear? So here, for example, if I ask you, at which frequency do we have the largest E? Anywhere here? Is it like here, perhaps? Or is it like here or here, right? That's the place where we reach, you can calculate the maximum weighted error by just examining the difference between your design and the ideal response. Okay? So now, the objective function that we write is the maximum of omega in certain intervals. And then we care about the maximum weighted error. And the whole problem is to because we want to minimize this. Okay? So in today's lecture, we are going to encounter minimax problem. Okay? We're going to minimize the maximum error. Okay? So minimize, that means that we need to search in a space. Okay? We need to search all possible You need to search all possible frequency responses. Yeah? Okay? Given that your filter has a length of 2n plus 1, and it is symmetric. Okay? So in other words, we are going to search all possible type 1 filters. All possible type 1 filters being symmetric like that. All possible, the space of all possible type 1 filters with symmetry. Search within that space the one special filter which minimizes the maximum weighted error. That's the problem statement. Is it cool? So far, so good? We're going to search this abstract space of all possible filters. The one and special filter which minimizes the maximum weighted error. Okay, so now we say this is the whole problem can be stated as this. So let me read it. Okay, so it's important that we know how to read this. Okay, the argument which minimizes the maximum error. Okay, that's the way I read it. We want to find an argument, meaning that the one and very special filter. That's an argument which minimizes the maximum weighted error, absolute valued. Finding that one special among all possible, the ensemble of all possible filters. Okay? So, but let me roughly say that then, what is the space of all possible filters? What is the space of all possible type 1 filters of length 2n plus 1? The space can be represented, can be encoded by its sample values. Okay? So for every filter, once we know the sample values, and this becomes a vector, right? This becomes a vector, let's say this is a vector that belongs to R of n plus 1. So the search space really is R n plus 1. That's our search space. We are searching all possible filters with each one with different sample values. Search within this R, this n plus 1 dimensional space. You know what I mean? N plus 1 dimensional space. So each filter can be represented by a vector. Think of it as a vector. So our search space is an n plus 1 dimensional vector space. Does that make sense? Is it making sense? Yeah. Search in that space, the one and very special vector that minimizes the maximum error. Okay? Minimize the maximum weighted error. Okay? So that's our problem formulation. That's so far so good? So for example, in this, so let's say this A omega is given, this A of omega corresponds to a vector in the space. Let's say some sort of vector gives you this A omega. And then the corresponding E, the corresponding error function, now we consider its maximum value. Maximum value, where is the error maximum? At which frequency? Let me give you a few candidates. Is it this frequency, or is it this frequency, this one, or this one? Where? Which one has a larger? It seems that the maximum error occurs either here or there. Can we agree on that? Okay, so let me elaborate. So here we need to specify, what do we mean F, okay? F, here, let me give you a further definition. Here, F is the what? The union of pass band and stop band. Okay, let's be more precise about this. F equals to, we either consider 0 to, no, cutoff frequency, that's a pass band and the stop band. So let's say F is the union, 连接, F is the union of pass band and stop band. We consider only pass band and stop band. So now with this definition, can you tell me where the absolute value of E reaches maximum within this frequency range plus that frequency range. Is it here or here? Is it here or here? Here or here? So I think it's here because we have a weight. Remember that we have a 3-time weight. Okay, so please also consider the weight. So even though this difference is smaller, but when you multiply by 3, maybe that difference becomes enlarged, become emphasized. Is that clear? So if this difference multiplied by 3, the result might be bigger than this difference, according to by inspection, by 用看的, by visualization, right? So that's the idea. So that gives you an idea. So now, that's why so we can hopefully that give you a feeling what's the meaning of W. W is sort of like I call a penalty factor. 你这我惩罚了, penalty factor. W, the meaning of W, you can say it is a penalty factor. 惩罚的 the penalty, right? 惩罚 In Chinese, 惩罚. It's a penalty factor. How much do you penalize error? Okay, so in this example, we penalize error more in the stop band than the pass band. That means that we're going to tolerate the ripple a bit more for the pass band than the stop band. Okay, here we have less tolerance, higher penalty, less tolerance. That's the meaning, okay, in this example. Of course, so that gives you some flexibility. Okay, as we'll see next, this will give us some flexibility as to adjust the ratio of ripples. Okay, but so far I've only told you the problem formulation, but we haven't touched on how to find that one and special filter, right? We haven't talked about that. But this is just the kind of definition of our loss function. Okay, our objective function that we're going to minimize. Okay, when we find the argument which minimizes the maximum approximation, the result is a very nice H vector. Okay, the result being, wow, we find the best one. Okay, the result, the return on the left-hand side of the equality, we can put this is the best one. Usually we use hat to denote something that's very special, something that's the best. Okay. Now this best filter is, so now we need to say, we are searching in the n+1 dimensional space, the one and very special argument that minimizes the maximum approximation error. Okay, that's the way we read it. Okay, 吗？大丈夫ですか？大丈夫ですか？はい。Okay, so that's the Japanese for is it okay? Does it make sense? All right, so next let's dig in more and talk about how are we going to find H. Okay. How are we going to find H? Before I jump to the next slide, turns out that we need to introduce some sort of change of variable. Change of variable. We are going to just interestingly define a change variable. We define cosine omega as a new variable x. That's the key point, okay? That's the key point. Introduce a change of variable. And as a result of change of variable, now we can talk about going from the omega domain to the x domain. And in the next few slides, we are going to mainly work on the x domain. Okay? So, but if you notice, cosine in the x domain, then what is cosine 0? DC, cosine of 0 is 1, right? So now DC becomes 1. This is DC, 0 frequency. DC corresponds to x equal to 1. Okay? And what is Nyquist? Cosine pi. What is cosine pi? Cosine pi is -1, right? So now we are going to actually the entire direction is going to go backward. Okay. On the right, we have low frequency. On the left, we have high frequency. That which correspond to omega, correspond to Nyquist frequency right here. Okay, so as a result, now we are going to design a low pass. If we're going to define a low pass filter, then it has a cutoff X and a stop X. Okay, so here is the stop band. Here is a pass band, and this is a schematic for ideal low-pass filter. So we are going to work in the X domain for some interesting reason. Okay, but this is just to give you a preview. Okay, is that fine? We're going to just 脑力转弯一下啊, try to just change our perspective by defining this change of variable. Now, low frequency becomes on the right, high frequency on the left, from DC to Nyquist. Okay, you bear with me? Actually, 0 is cosine. Yeah, you can say here, of course, 0, x0 correspond to omega of pi over 2. Okay, but otherwise we introduce this transformation. So let's say now this is our desired, desired response in the X domain. Okay, in the X domain. And a bit more. So the reason we want to work in the X domain is by observation right here. Okay, I think I also have it in the next slide. I also have it in the next slide. Define this change of variable. And note that A of omega, the result of our design, the DTFT of this FIR filter, the frequency response, of course, can be written as, we've seen that it can be written as this expression. But note that now, after defining X to be cosine omega, turns out that this response can be written as a polynomial of X. And the reason is because each cosine n omega, cosine n omega can be written as a polynomial of cosine omega. So that's something, if that's something new to you, please learn this, okay? It turns out that actually this polynomial is called the nth order Chebyshev polynomial. Chebyshev polynomial, for example, T2x. What is cosine 2 omega? Cosine 2 omega, for example, so it turns out that cosine n omega, each cosine n omega, omega n doesn't matter, right? Each cosine n omega can be written as a polynomial of cosine omega. So cosine n omega is by definition Tn cosine omega. Okay? For example, this is actually pretty simple. For example, we all know that cosine 2 omega equals to what? Cosine 2 omega equals to cosine square omega minus sine square omega, right? Which in turn equals to 2 cosine square omega minus 1. So therefore, T2x equals to 2x squared minus 1. T2. So it's something very simple, okay? If I develop further, cosine 3 omega, does anybody know the formula for cosine 3 omega? We have no coach. Is it right? So again, cosine n omega is a polynomial of cosine omega, right? So it's just we have seen two cases. Therefore, T3, this polynomial, the third order Chebyshev polynomial equals to 4x cubed minus 3x, and so on. Okay. So I hope you are convinced that, but at least by intuition, every cosine n omega can be expressed as a polynomial of cosine omega. And what is cosine omega? Cosine omega is x. Okay. So what's the implication? Any possible FIR response, if our length is from -n to n, if we have 2n plus 1 samples, all possible type 1 frequency responses can be every one of them can be written correspond to a polynomial, an nth order polynomial of x. So that allows us to change our search space from the space of Rn plus 1 to the space of polynomials. So that's an important consequence. Okay? After this change of variable, we go to the x domain, and our search space becomes the set of real coefficient nth order polynomial. It's a vector space. Now, this notation may require some elaboration. Okay, so let me read this. So now, knowing that every possible frequency response corresponds to a polynomial, so now we change our search space. We're going to search the best polynomial, the one and very special polynomial in the set of all possible nth order polynomials. Okay, Pn x. A bit of a note about notation. So here, let me erase some simple stuff. So now you know that cosine 2 omega is a polynomial of cosine omega. Cosine 3 omega is a polynomial of cosine omega. But now, let me tell you a bit more about the notations. We're going to search in this space. So here, P n with R, okay, is the vector space of all possible that contains. I should say that contains all possible nth order real coefficient polynomials. You know what I mean? The space of all nth order or lower order polynomials, so to speak. Okay, we're going to search within this space. Okay, we're going to find the one polynomial up to nth order, which still the argument which minimizes the maximum approximation error. Okay, so here W the weight, D the desired response, and P is the result of our design. Is that clear? Let's just point to P is here. P is our design. D stands for desired. Okay. The desired response. So this desired response is. Let me change my notation. Now the desired response is denoted as D. I forgot why I emphasize P here, but just to. I forgot why I have a subscript. But this is a desired response in the X domain, okay, after the change of variable. Desired response is 1 in the passband, 0 in the stopband. Okay? That's the desired. Now still we calculate we examine the difference between your design. Your design is a frequency response expressed as a function of X. Okay? This is a frequency response. That's a frequency response, right? But after change of variable, the frequency response can be expressed in the X domain. Okay? P is your frequency response. That polynomial is the frequency response. Is that clear? We're going to try to construct a P that minimizes weighted error in the union of passband and stopband. Is that clear? So now a bit of about notation here. This is a sort of sloppy notation. F, what is F? F is the intersection of stopband and passband, right? But now what do I mean cosine F? F is the set. This is a union of two intervals. So cosine F means basically, it's a sort of a sloppy notation, so please bear with me. Cosine F is f after mapping by cosine. Okay, cosine f now, if you will, should be the union of the passband and stop band. Okay, so basically cosine f is the passband and stop band after change of variable. Just a sloppy notation. 不是很严谨的 notation. It's not the most rigorous notation, but please bear with me for simplicity. Search within all possible design a polynomial which is your frequency response that minimizes the maximum approximation weighted within the range of stop band and pass band in the X domain. Now everything becomes in the X domain. And we're going to find one polynomial which best suits our purpose. Okay? So that's the kind of spirit of optimization, right? Find something that is the best. That's the meaning optimization. Optimization is 最佳化 in Chinese. 最佳化. We find the 最佳 the best. Finding something that's the best. Okay, that's the spirit. Search within all possible polynomials the one that is the best. The argument which minimizes our error function. And call it p hat. Hat means something that's the best. Is that clear? That's a problem formulation. Now we're going to work in the domain of polynomials. To have now changed the filter design problem into a polynomial approximation problem. Should I say that again? We change the filter design problem into polynomial approximation problem. 变成多项式的逼近的问题。We change our problem. We have transformed our problem into a problem of finding a polynomial, a best polynomial, which approximates our desired frequency response. Okay? All right. Questions so far? I actually have a question. So, two questions. Yeah. For T3, does anybody remember T4? What is T4x? Cosine 4 omega equals to what? Does anybody know the answer? I don't. I don't memorize that. But is anybody memorizing T4? Your AI probably can answer that in a second, right? But nobody. So it becomes tricky. You see what I mean? How about T5? And in general, if you are designing a filter of length 32, wow. Does that mean we need to consider cosine 16 omega? And what is that polynomial? You can imagine that it becomes very dirty, right? By hand. It becomes very dirty by hand, okay? So I'm going to just, hopefully this is just something for you to consider, okay? If I ask you to write a program which returns to you a Chebyshev polynomial of any given order, can you do that? Yeah, so actually you can do that, okay? You can do that by iteration, yeah. So so maybe next week in our follow-up discussion we can work on that. Yeah. So that's one first question. But suppose that, so there's an iterative relation. If I remember, the iterative relation goes this way. It's not easy to see that. Cosine n plus 1 omega I think it's this, cosine n minus 1 omega. The hint is here. When you sum them up, that equals to what? 2 cosine omega cosine n omega. So that's a hint. So we can always express cosine n plus 1 omega in terms of cosine n minus 1 omega, cosine omega, and cosine n omega. and that gives you Tn plus 1 x equals to 2x Tnx minus Tn minus 1x. Check it out, okay? So this is a hint. Actually, there is such a formula that iteratively, 递回式的, which successively, iteratively give you the next Chebyshev polynomial in terms of the previous two polynomials. Okay, so now you see there's a chance you can write a program, a script, right? Okay, write a C code for that. Okay, that's my first question. And second question, okay. So knowing that we already know that our next step to describe how to find the best polynomial, okay? How to find the best polynomial. So the result will be, I can tell you, the result will be sort of equal ripple. 我每次都画得不太好啊。Let me just move the stop band edge right here. The result should be something like that. The result will be equal ripple. So that's kind of a preview. The result will give you equal ripple in the pass band and equal ripple in the stop band. Equal ripple. The ripple up and down will be like all equal. Okay. So that's what we're going to discuss next. Okay. So let's say, so this actually, you can imagine that this really is a sort of polynomial. This can be a polynomial, okay? This really can be a polynomial, but then maybe after that it goes down. Maybe after that it goes up, okay? So this really, within -1 and 1 is a polynomial with equal ripple, but outside we don't care. Outside is outside. Outside does not correspond to any frequency. Okay, so we only care about this polynomial's behavior within the range of -1 and 1. Outside can go wild, we don't care, okay? So we're really looking for a polynomial which might look like that, okay? So suppose that we can indeed, somehow there's an algorithm that gives you this polynomial. And now the next question becomes, now you have the best P of x. How do you go back to the omega domain? That becomes a bit harder, right? We know that when we are given the response in the omega domain, we know how to convert cosine into Chebyshev polynomials. Well, how do we go back? Once you find the best polynomial approximation, how do you go back? Technically, that remains a challenge, okay? It's not too hard, it's doable, but it's not so straightforward. 并没有很简单啊. Can we agree on that? It's easier to come from here to here, but harder to go backward. But I think there's a one-to-one. I'm pretty sure there's a one-to-one correspondence. Yeah. There's a one-to-one correspondence, but computationally, how do you achieve that? That might be a bit more challenging. Okay. You get a feeling? Going from here to here is easier, right? Now you know the Chebyshev polynomial. Going from here to here is easier, but going back, the other direction might be a bit more challenging. Okay. But I do believe that I think I'm correct. I'm right. There's a one-to-one correspondence between every polynomial and all possible frequency responses. One-to-one correspondence. So that strengthens our confidence that we are going to work on polynomial approximation next. Okay? Because there's a one-to-one correspondence between the two spaces, between this H space and that space, right? The P space and H space. Okay? So far so good? So we have about 10 more minutes. So now this is a pretty interesting theorem that gives us some hint. What does the optimal solution look like? How does it look like? Okay? And this theorem has a name, the alternation theorem. 交错的, 交错的, alternation, alternate, 交错, alternating series, 交错级数. The alternation theorem, 交错的定理. So what does it say? So let's say Fp is a union of disjoint closed interval of real axis x. For example, we have two intervals, two disjoint intervals of pass band and stop band. So that's one example. let's say f is the intervals of our interest. Okay? And let's say we are just let's say that again. We are going to find the best polynomial which minimizes the maximum approximation error. It turned out that the theorem goes that the necessary and sufficient condition for a unique best solution is that best solution must give you at least n plus 2 distinct values of x. Let's order it into n plus 2, right? n plus 2. We can find at least n plus 2 values, x1 to xn plus 2, such that the error alternates between neighboring points. Okay? Such that the weighted error becomes is positive for one x, then it's negative for the other x. So that's why we have this name, the alternation theorem. The error alternates between these distinct values, plus or minus, they alternate, okay, when we go from the x1 to xn plus 2. But then at each of these places, the error O equals to the error is maximized at all the n plus 2 distinct values. Let me say that again. When the error alternates for sure with the minus sign here, but then for each of them, the maximum is simultaneously reached, either plus or minus the maximum weighted approximation error. So where EP is defined as W times the difference, right? Okay? So this takes a while to digest. Takes a while to digest. Maybe we should copy the result. Let's copy the result, all right? And in the next page, I think that we have a few examples. Let me copy the results, because you have the privilege to slide back and forth on your iPad, but I need to, let me erase all my writing right here. And then I'm going to copy this alternating theorem right here. Okay, so let's say the best solution has this property. You can find x1, x2, distinct values, and you order them from left to right, n plus 2, such that when we evaluate the error function in the polynomial space equals to the weight times the difference, okay, the approximation error, desired response, and minus our frequency response. So that's the error, and this error can be positive or negative, right? Because we don't have absolute value. Okay. But now, alternating theorem tells us that the best P of x that you find is gonna have the following property. That you can find this, okay? You can find all these n plus 2 distinct points such that the error evaluated at the current point equals to the error evaluated at the next point, but with the minus sign, the error alternates between these distinct points, and the error is simultaneously maximized. The error on these n plus 2 points are simultaneously maximized. The maximum error is simultaneously reached at n plus 2 different points. Is that clear? The best solution turns out it has to have this property. It's a theorem which we are going to skip the proof. Okay, we're going to skip the proof, but as the result of the proof, the highlight of the proof, this theorem tells us that no matter how you find the best one, okay, but the best one has this property. No matter how you find it, okay, how to find is a separate issue, an even harder issue. But the best one, mathematically, will have this property of error alternating between neighboring points, and the error is simultaneously maximized, 同时被最大化. The error is simultaneously maximized among at least n plus 2 different points. Okay, so that's a kind of result. The result of this theorem. It will be probably clearer if we see the next picture. So now let's try to tell. Which one, so now we have 3 polynomials, okay? They all look like the same order. 3 polynomials, and if I ask you what's the order of the polynomial, can anybody tell me? What's the order of the polynomial? 这是几次的多项式? Does it look like it looks like a 5th order polynomial to me. Because that's 3rd order, right? And that with one more up and down, that could be like by illustration, as an illustration. 只是画图啦, but it looks like all of them, it makes sense that they're all, let's assume that all of them are 5th order polynomials. Okay? So in this example, for example, n equals to 5. Okay, let's assume, keep in mind. Let's assume that we are looking at 3 different 5th order polynomials. Okay? And are we designing a high pass or low pass filter? You remember to the left we have high frequency, right? So it seems like here we have the pass band, and that's the stop band. So we are actually designing a high pass filter right here. Okay? But it doesn't matter. Kind of the interesting thing about optimal design is that it doesn't matter. We don't need high pass to low pass transformation. So sort of the design now it has been unified in this new framework. 在新的方法上面是同整的, so we don't need to first design low pass, then apply low pass to high pass transformation. We don't need to do that anymore. Okay. So in this example, the textbook is trying to explain a design of high pass filter. Okay. But then, so now we have 3 approximations. These 3 polynomials look a bit different. Okay. They look similar, but they are not exactly the same. Okay. Can anybody tell me where do they differ? Where do they differ? So for example here, right? This is not touching. Where this one is touching. Okay, so that's one difference. Okay. What else? What else? Oh, here it's touching, but here there might be some room for improvement. Do you see what I'm saying? Maybe we can push this curve a little bit to the right and then further reducing the ripple. That's the idea. We're going to find out, keep fine-tuning the polynomial until this one looks, can we agree that this one looks better than all the other 2? It seems that this one, within all the possible 5th order polynomial, is all it's doing is a very good job. No room for improvement anywhere. That's the idea. That's the feeling. 这是个感觉啦. So the way I say it, this one indeed looks better than the other 2. Because here there's room for improvement, here that's definitely some room for improvement. Maybe we can just make this one larger while make this one smaller and simultaneously improve the entire, reducing the maximum ripple. Okay? So this one definitely has a room for improvement. That's the kind of feeling. That's the kind of feeling. This space, this gap right here means a room for improvement. 还有改善的空间, a room for improvement. Similarly here, that's a room for improvement. Maybe we can make these ripples smaller by make this error larger. So why do I say that? So can we sort of agree at least temporarily, that this one looks better than the other two. If so, how does that correlate to this theorem? This theorem tells us a way to check the progress, to check if the condition has been satisfied. So I'm going to tell you next that these two do not satisfy that condition yet. Okay? Why not? You see that here, assume that here the maximum error is simultaneously reached in 1, 2, 3, 4, 5 different places. Actually, 6 different places. Okay? Allow me to put it. I'm going to. Yes, TA, please help me clean up. Okay, here is yet another place where the. Here is yet another place where. Yet another place where the error reaches maximum, right? But then, I'm sorry. No, yeah, 1, 2, 3, 4, 5, 6. We have 6 different places where the error has been simultaneously maximized, okay? Where the error simultaneously reaches maximum. But the sign do not alternate. Here is under, above, under, above, under. We skip that, but under. So this polynomial does not satisfy this property. This property is not satisfied by this very polynomial. That's the way we check. You see? Because there's each next point need to alternate, change the sign, okay? When you jump from x1, so seriously, this is x1, x2, 3, 4, 5, 6, okay? But the 5th and 6th one, we see that at both points, the approximation is under, okay? Not above. Therefore, the sign is not alternating right here, so that theorem is not completely satisfied, okay? So that's what we check. So our conclusion should be that this one is optimal, not optimal yet. That becomes our conclusion simply by checking the sign. Under, above, under. You see what I mean, under and above. This is ideal response, right? Pass band, stop band. So here is undershooting, overshooting, undershooting, over, under. This is over again, but he's under, okay? And the maximum error is simultaneously reached at 6 different points. First of all, there's no sign alternation between these 2 adjacent points. And secondly, the maximum error is reached simultaneously only at 6 different places, but we need at least 7. Okay, we need 7. But the maximum error is simultaneously reached at only 6 different places. So that too violates the theorem. So that gives you a hint. That gives you a clue that this polynomial is not the best. Not yet the best. There's still room for improvement. So that's the way we look at this figure. Okay? And similarly, you can count here. Seems that, 1, 2, 3, I think this is 4, 5, 6. Okay? Again, 6 different places, but here 2 problems persist. First of all, we only have 6 points. And secondly, here is under, and next one is also under. There's still room for improvement right here. Okay, so we need 7 points. And we need the sign to alternate between under and above, under. Again, under, so yeah, this one is not optimal yet. Yeah. But how about finally this one? It looks like we have over, under, over, under, over, under, over, under. 8 different points. That's good. Yeah, 8 is even more than. We actually have the case of 1 extra alternating point. Okay, it has at least 7 different points with alternating error. When we go to the next point, from above to under, above to under, above, under, above, under. So the theorem seems that the property has been perfectly satisfied. Okay, so this one we must conclude that because of that theorem, this one is the optimal polynomial approximation for this high-pass design, okay? So I think we're about over time, but the next thing is just an illustration of the penalty factor. Okay, penalty factor. When the weight function is large, then when you finally find the best approximation, it gives you a smaller ripple, which means that our tolerance for the pass band is smaller in this case than the stop band. Stop band ripple being larger. But this one, again, what is the order, you think? What's the order? That's 3, 5, 7. It looks like a 7-order polynomial. Okay? And we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It seems that in this drawing, we have 10 alternating points. For a 7th-order polynomial fitting is good. This is optimal. Another example. But now I'm going to skip the algorithm part. So there is a famous algorithm by Parks-McClellan by the name. So we're running out of time, so maybe we can talk about it next time when we meet. Okay, next Wednesday. All right, so that'll be all. And thank you for staying with me. Have a nice weekend.